Before the universe existed as we know it, before the formation of atoms, stars, planets, or even the basic ingredients of space and time, there was a state we describe, not casually but mathematically, as nothing. This does not mean an empty space, because space itself did not yet exist. Rather, it refers to the absence of physical laws, no dimensions, no energy, no matter. Conditions beyond ordinary comprehension. From this indescribable state, a moment occurred, what modern science calls the Big Bang, not an explosion in space, but the sudden emergence and expansion of space-time itself, carrying with it the raw essence of the universe energy, the seeds of matter, and the forces that would govern everything to come. Over billions of years, that event gave rise to every star burning in the night sky, every grain of sand on Earth, and eventually every living cell within our bodies. At its core lies the most profound question humanity has ever asked. Not merely where we exist in the cosmos or what we are made of, but how existence began at all. This question sits at the intersection of many disciplines. Physics seeks the governing laws of this beginning. Astronomy observes the traces of those early moments. Mathematics provides the language to describe them. Chemistry explains how matter formed. Philosophy attempts to interpret the meaning. And even the study of consciousness is pulled into the discussion as we try to understand how beings capable of asking such questions emerged from cosmic chaos. This chapter sets out on a scientific journey to uncover that origin story, not by relying on ancient myths or untestable beliefs, but through rigorous investigation, observation, measurement, and theory. The pursuit is not merely to collect facts, but to understand how everything, from galaxies to human thoughts, arose from a universe that began in a moment still shrouded in mystery. Since the earliest chapters of human existence, long before the invention of writing, mathematics, or scientific instruments, our ancestors gazed upward at the night sky and felt a profound sense of wonder. They saw countless tiny points of light, stars, and questioned what they were, why some moved while others remained fixed, why the sun rose every morning and disappeared every evening, why seasons changed, and ultimately, where everything came from. These questions were not merely expressions of curiosity. They were humanity's first steps toward science, the earliest attempts to understand the world through observation and reasoning. This innate drive to question the cosmos is woven deeply into human nature. To study the universe is to continue a tradition that began with the first conscious minds that looked at the stars and tried to make sense of their place beneath them. Modern cosmology still seeks answers to those same ancient questions, though now armed with powerful tools. Telescopes that can look back in time, mathematical models that describe the laws of nature, and physical theories that explain how matter and energy behave. We ask, where did the universe originate? Why do the laws of physics have the precise values that allow stars, galaxies, and even life to exist? Did life arise because it was destined to? Or are we simply a fortunate accident in a vast cosmic lottery? And perhaps one of the most emotionally charged questions, are we alone, or does life exist elsewhere among the stars? These questions are not abstract. They connect directly to our identity. Every element in our bodies, every structure on Earth, every force shaping our lives ultimately emerged from the cosmic processes we seek to understand. By studying the universe, we learn not only about distant galaxies and ancient explosions, but also about ourselves, because we are, at the most fundamental level, products of the cosmos. Every atom within your body, whether the carbon forming your DNA, the oxygen flowing through your lungs, the nitrogen in your proteins, or the iron circulating in your blood, originated in the heart of a star. These elements did not exist at the universe's beginning. They were forged billions of years later through the process of nuclear fusion, in which the intense heat and pressure inside massive stars fused simple atoms like hydrogen and helium into heavier elements. When those ancient stars neared the end of their lives, many exploded as supernovae, scattering their enriched material across the cosmos. Over time, that stardust condensed under gravity to form new stars, planets, and eventually living organisms, including us. This is not poetic metaphor. It is a precise scientific truth. We are literally made of star-created matter. To understand the universe, therefore, is to explore our deepest origins, not just as humans or as life forms on Earth, but as parts of a cosmic evolution stretching back nearly 14 billion years. Our family tree does not begin with our species, nor even with the first life on Earth. It goes further back, linking us to the formation of our planet, to the birth of our solar system inside the Milky Way, to the earliest galaxies that formed soon after stars ignited, and ultimately to the extraordinary moment of the Big Bang. Studying the universe reveals how the raw materials of life emerged from simple primordial elements, how planets like Earth condensed from cosmic dust, how galaxies organized themselves into grand structures shaped by gravity and dark matter, and how order gradually arose from the initial chaos of creation. In doing so, we uncover not just a scientific narrative of physical processes, but the most comprehensive story ever told, one that connects all things, from the smallest cells to the largest cosmic structures, into a single, breathtaking continuum. It is, quite literally, the story of everything. Unlike the controlled laboratories we build on Earth, the universe offers environments so extreme that we cannot reproduce them with any technology currently available. Neutron stars, for example, are remnants of collapsed massive stars whose matter is packed so densely that a teaspoon of their material would weigh billions of tons, far beyond anything we can generate or even fully visualize on Earth. Black holes push physics to its breaking point, containing gravity so powerful that not even light can escape, and their boundaries, the event horizons, force us to confront the fundamental nature of space, time, and information. Quasars, powered by supermassive black holes consuming surrounding matter at furious rates, shine brighter than entire galaxies and serve as cosmic beacons illuminating the distant universe. Meanwhile, the early universe itself existed under conditions of unimaginable temperature and energy, far greater than anything achieved in particle accelerators, making it the ultimate testing ground for the laws of physics. By observing and modeling these extreme environments, scientists can explore nature's limits and examine theories that cannot be tested terrestrially. Many of the greatest breakthroughs in modern science, from the development of quantum mechanics to Einstein's theory of relativity, were inspired by astronomical observations. The sky became a laboratory that reshaped our understanding of reality. This is why cosmology is not a separate field floating outside physics. It is physics, just extended to the grandest possible scale, where the smallest quantum phenomena and the largest cosmic structures meet. The universe is our ultimate experimental arena, revealing truths that no machine on Earth could uncover, stretching our knowledge toward the very boundaries of existence. Exploring the universe does more than just satisfy human curiosity. It actually drives technological innovation that, reshapes our everyday lives. Telescopes, which were originally developed to peer deeper into the cosmos, have led to the creation of advanced materials and imaging technologies, including those charge-coupled device sensors that now power the cameras in our phones. Space missions, which have to operate in those extreme environments, far from Earth, have really pushed the boundaries of computing, engineering, and robotics, resulting in faster processors, more reliable electronics, and, well, sophisticated communication systems. Cosmology itself has inspired the development of advanced mathematical tools, which enable precise models of complex systems both out in space and here on Earth. Even technologies we tend to take for granted, like the Global Positioning System, or GPS, rely directly on Einstein's theories of relativity, correcting for time dilation caused by satellites orbiting Earth, so they can provide us with accurate positioning. Other examples abound. Satellite communication depends on our understanding of orbital physics, while modern electronics, from semiconductors to quantum devices, are rooted in discoveries from quantum mechanics, much of which was initially motivated by astronomical observations. In essence, by studying the universe, we not only deepen our understanding of the cosmos, but also develop better tools, more advanced engineering solutions, and a richer comprehension of the fundamental principles governing reality. Benefits that, honestly, permeate every aspect of modern life. The universe is vast beyond anything our minds can easily grasp. Within the observable universe alone, there are more than 200 billion galaxies, each containing billions of stars, along with countless planets, nebulae, and other cosmic structures. In the grand scale of this immense cosmos, we are an extraordinarily tiny species living on a small, rocky planet, orbiting an unremarkable star in a moderately sized galaxy. This perspective, provided by cosmology, is deeply humbling. It reveals that humanity does not occupy a privileged or central position in the cosmos, and that the Earth is just one small part of a much larger, complex system. Yet, in this same realization lies a profound paradox. It also makes us remarkable. Despite our insignificance in scale, we are among the very few entities known to have evolved the ability to observe, analyze, and comprehend the universe itself. Out of this vast cosmic ocean, life arose with consciousness capable of asking questions about origins, structures, and the laws that govern everything. Cosmology teaches us both humility and wonder. We are not at the center of existence, yet through science, reasoning, and exploration, we have the extraordinary capacity to understand the very universe from which we emerged. One of the most fascinating aspects of studying the universe is that the more we uncover, the more questions arise. For example, astronomers discovered nearly a century ago that the universe is expanding, with galaxies moving away from each other over vast distances. Yet even this revelation was only the beginning. Decades later, observations of distant supernovae revealed a startling truth. The expansion of the universe is not slowing down, as once expected, but accelerating. This acceleration appears to be driven by a mysterious force we barely understand, now called dark energy, which seems to dominate the cosmos and counteract the pull of gravity on the largest scales. Each discovery, instead of closing the book on a cosmic question, opens entirely new chapters of inquiry, revealing deeper layers of complexity and subtlety. This endless chain of discovery, where each answer uncovers further mysteries, propels scientific progress, pushing humanity to develop new theories, build more precise instruments, and expand the boundaries of knowledge. In exploring the universe, we realize that understanding is not a destination, but a continuous journey where the pursuit of questions itself drives the evolution of science. Understanding the origins of the universe is not merely an academic pursuit. It is essential for predicting its ultimate fate. Cosmologists have developed multiple scenarios based on the laws of physics and observations of cosmic expansion. One possibility is that the universe will continue to expand indefinitely, gradually cooling and fading into a state known as the Big Freeze, where stars burn out and matter becomes ever more diffuse. Alternatively, gravity could eventually halt and reverse the expansion, causing the universe to collapse back into a singular state in a dramatic event called the Big Crunch. A more extreme possibility, the Big Rip, suggests that accelerating expansion driven by dark energy could eventually tear galaxies, stars, planets, and even atoms apart. Some models propose a cyclic universe, in which cosmic expansion and contraction repeat endlessly over incomprehensible timescales. These scenarios illustrate a profound connection between our origins and our destiny. The same physical laws and processes that govern the universe's birth will shape its end. To understand where the universe is heading, and ultimately the fate of everything within it, we must first understand where it came from. A journey that links creation, evolution, and cosmic destiny into a single, awe-inspiring continuum. Cosmology is the branch of science dedicated to understanding the universe at its grandest scale, encompassing its origin, its evolution over billions of years, its large-scale structure, and ultimately, its fate. While closely related to astronomy, which focuses on observing stars, planets, and galaxies, cosmology goes further by seeking to explain how these cosmic structures formed, why they behave as they do, and what underlying physical laws govern their development. It asks the largest and most profound scientific questions imaginable. How did the universe begin? What is it fundamentally made of? How do its various components interact and evolve over time? And what is the ultimate destiny awaiting all matter and energy? To address these questions, cosmology integrates multiple disciplines. Physics provides the laws that govern motion, energy, and forces. Mathematics offers the precise language to model and predict cosmic phenomena, and observational astronomy supplies the data needed to test and refine those models. In this way, cosmology is not just a subfield of science. It is a comprehensive framework for understanding everything in the universe, from the tiniest particles to the largest clusters of galaxies, offering a systematic narrative of existence itself. While astronomy and cosmology are closely related, they differ in scope and purpose. Astronomy primarily focuses on observing and understanding individual celestial objects, stars, planets, nebulae, and galaxies, analyzing their properties, movements, and interactions. Cosmology, on the other hand, studies the universe as a whole. Its origin, how it has evolved over billions of years, its large-scale structure, and its ultimate destiny. In other words, astronomy tells us what exists within the universe, providing detailed knowledge of its components, while cosmology seeks to understand the universe itself, how all these components emerged, interact, and change over time under the laws of physics. Astronomy offers the pieces of the puzzle, whereas cosmology seeks to see the complete picture, revealing the narrative of existence from the Big Bang to the far future. Cosmology rests on several key components that together allow us to understand the universe at its grandest scale. At its foundation lies space-time, the four-dimensional fabric that unites space and time into a single dynamic entity, whose curvature and expansion govern the motion of matter and energy. The universe itself is composed of different forms of matter and energy, with ordinary matter, the atoms making up stars, planets, and life, constituting only about 5% of the total, while the enigmatic dark matter, invisible yet detectable through its gravitational effects, makes up roughly 27%, and the mysterious dark energy, driving the accelerated expansion of the cosmos, comprises approximately 68%. Understanding how all of this behaves requires physical laws such as Einstein's general relativity, quantum mechanics, thermodynamics, and nuclear physics, which together describe phenomena from the smallest particles to the largest cosmic structures. On the largest scales, matter organizes into the cosmic web, with galaxies forming groups, clusters, superclusters, and filaments that span vast distances, giving the universe its large-scale structure. Finally, cosmology considers the evolutionary timeline of the cosmos, beginning with the Big Bang, followed by the formation of the first stars and galaxies. The emergence of planetary systems like our solar system, the birth of Earth, and ultimately the appearance of life. Together, these components provide a framework for understanding how the universe came to be, how it is structured, and how it continues to evolve across billions of years. Cosmology rests on several key components that together allow us to understand the universe at its grandest scale. At its foundation lies space-time, the four-dimensional fabric that unites space and time into a single dynamic entity, whose curvature and expansion govern the motion of matter and energy. The universe itself is composed of different forms of matter and energy, with ordinary matter, the atoms making up stars, planets, and life, constituting only about 5% of the total, while the enigmatic dark matter, invisible yet detectable through its gravitational effects, makes up roughly 27%. And the mysterious dark energy, driving the accelerated expansion of the cosmos, comprises approximately 68%. Understanding how all of this behaves requires physical laws such as Einstein's general relativity, quantum mechanics, thermodynamics, and nuclear physics, which together describe phenomena from the smallest particles to the largest cosmic structures. On the largest scales, matter organizes into the cosmic web, with galaxies forming groups, clusters, superclusters, and filaments that span vast distances, giving the universe its large-scale structure. Finally, cosmology considers the evolutionary timeline of the cosmos, beginning with the Big Bang, followed by the formation of the first stars and galaxies, the emergence of planetary systems, like our solar system, the birth of Earth, and ultimately, the appearance of life. Together, these components provide a framework for understanding how the universe came to be, how it is structured, and how it continues to evolve across billions of years. Mathematics is the essential language of cosmology, allowing scientists to model the universe, make predictions about what should be observed, and build detailed simulations of cosmic phenomena that span billions of years and, honestly, unimaginable distances. Through mathematical formulations, cosmologists can test theories under conditions far beyond what can be physically reproduced on Earth. For example, the Big Bang theory uses equations from general relativity to describe the rapid expansion of space-time from an initial singularity, while the inflation theory employs precise mathematical models to explain the sudden, exponential growth of the early universe. Dark matter models rely on calculations to predict how unseen matter influences galaxy rotation and cosmic structure formation, and string cosmology explores how fundamental strings vibrating in higher dimensional space could explain the underlying laws of physics. In every case, theory and observation work hand in hand. Mathematics provides predictions, which astronomers test through telescopes and detectors, refining models to match the actual universe. This interplay allows cosmology to move from abstract equations to a detailed, predictive understanding of reality on the largest scales imaginable. The universe is not a static entity. It is dynamic, constantly evolving across vast spans of time. Much like a living organism that is born, grows, matures, and eventually dies, the universe itself passes through distinct stages, each governed by physical laws and cosmic processes. From the instant of its birth in the Big Bang, to the formation of the first atoms, stars, and galaxies, and onward to the emergence of planetary systems and life, the universe has a complex and continuous life cycle. By studying its evolution, cosmologists can trace how matter and energy interact over billions of years, revealing patterns of growth, transformation, and eventual decline on cosmic scales. Understanding these stages is crucial because it provides a framework to interpret not only the present state of the cosmos, but also its history and potential future, allowing us to see our place within an ever-changing, living universe. The universe began approximately 13.8 billion years ago. But this beginning was unlike any event we experience in everyday life. It was not an explosion in space, as if something detonated within a pre-existing void. Rather, it was the rapid expansion of space itself, stretching the very fabric of space-time from a state of unimaginable density and temperature. At the very first moment, known as θ equals 0, all matter and energy were compressed into an infinitesimally small point. Or at least, that is how our current theories describe it. In this state, called a singularity, density and temperature approach infinity, distances shrink to zero, and the familiar laws of physics, including general relativity and quantum mechanics, no longer hold. Importantly, this singularity is not a physical object in the universe. It is a signal of our current ignorance, a boundary beyond which our mathematical models fail, rather than a tangible entity we can observe. It marks the transition from nothing as we understand it, no space, no time, no matter, into the expanding universe that would eventually give rise to atoms, stars, galaxies, and life itself. Studying this singularity challenges scientists to develop new theories that unite gravity with quantum mechanics, often called quantum gravity, to describe how the cosmos could emerge from conditions so extreme that conventional physics collapses. This earliest instant, the origin of everything we know, sets the stage for all subsequent cosmic evolution, from the formation of the first particles and atoms to the vast cosmic structures we observe today. It is both a scientific frontier and a profound reminder of how little we truly understand about the very beginning of reality. In the earliest fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion known as cosmic inflation. So fast that, for a brief moment, distances expanded faster than the speed of light. During this period, the universe grew from a size smaller than an atom to macroscopic dimensions almost instantly, stretching space itself in a way that really defies everyday intuition. Inflation had profound consequences for the structure of the cosmos. It smoothed out irregularities, creating a universe that is remarkably uniform and isotropic on large scales, and it flattened the geometry of space, making the universe appear flat in the sense predicted by general relativity. Despite this overall smoothness, tiny quantum fluctuations, minute variations in energy density at subatomic scales, were stretched to cosmic proportions during inflation. These fluctuations became the seeds of galaxies and clusters of galaxies, providing the initial density variations that gravity would later amplify, ultimately shaping the intricate cosmic web of stars and galaxies we observe today. Without inflation, the universe would look very different, irregular, curved, and lacking the large-scale structure that allows galaxies, stars, planets, and life to exist. This brief but extraordinary epoch set the stage for everything that followed, linking the smallest quantum events to the grandest structures in the cosmos. After the universe expanded and cooled following inflation, it entered a period where fundamental particles began to form and organize. In the first microseconds, quarks, the building blocks of matter, combined under the influence of the strong nuclear force to create protons and neutrons, the components of atomic nuclei. Electrons, the lightweight charged particles, formed slightly later as the universe continued to cool. During the next few minutes, these protons and neutrons began fusing in a process called primordial nucleosynthesis, creating the first simple atomic nuclei, primarily hydrogen, the most abundant element in the universe, and helium, along with trace amounts of lithium and beryllium. This process was extremely brief, lasting only a few minutes, because the universe continued to expand and cool rapidly, eventually making nuclear fusion inefficient at that time. Primordial nucleosynthesis set the initial chemical composition of the cosmos, providing the raw materials for the first stars to form hundreds of millions of years later. These early elements became the foundation for everything that followed, from stars and galaxies to planets, oceans, and eventually, life itself. By understanding this stage, cosmologists can trace the chemical origins of the universe and test theoretical models against precise measurements of elemental abundances observed today. Around 380,000 years after the Big Bang, the universe had expanded and cooled sufficiently for a pivotal transformation to occur. Until this moment, the cosmos was a hot, dense plasma of free protons, neutrons, and electrons, constantly scattering photons, meaning light could not travel freely. Every photon was immediately absorbed or deflected. As the temperature dropped to roughly 3,000 Kelvin, electrons combined with nuclei to form neutral atoms, primarily hydrogen and helium, in a process called recombination. This decoupling of matter and radiation allowed photons to travel unhindered for the first time, essentially turning the universe transparent. The light released during this epoch has been traveling across space ever since and has cooled over billions of years due to cosmic expansion, now observed as the cosmic microwave background, a faint, uniform glow that fills the universe. The CMB is a direct relic of the early universe, providing a snapshot of its conditions at this critical stage. By studying its tiny fluctuations, scientists can trace the seeds of galaxies and large-scale structures, making the CMB one of the most powerful tools for understanding the universe's origin, composition, and evolution. After the formation of neutral atoms, the universe entered a period often referred to as the Cosmic Dark Ages, lasting from roughly 380,000 years to several hundred million years after the Big Bang. During this epoch, no stars or galaxies had yet formed, leaving the cosmos shrouded in darkness despite being filled with matter. The universe was dominated by diffuse hydrogen and helium gas, and photons streamed freely but carried little energy, making the cosmos invisible to the naked eye. In this quiet, dark period, gravity began its slow but relentless work, pulling together slight variations in matter density, remnants of tiny quantum fluctuations from inflation. Over millions of years, these overdense regions grew, gradually attracting more gas and forming the first clumps of matter that would eventually ignite as stars. The Dark Ages were, therefore, a crucial stage, a time of preparation, where the seeds of cosmic structure were planted, setting the stage for the brilliant emergence of the first luminous objects in the universe. Approximately 200 to 400 million years after the Big Bang, the universe emerged from its dark ages with the formation of the first stars, marking a critical turning point in cosmic history. These early stars, known as Population 3 stars, were massive, composed almost entirely of hydrogen and helium, and lived short, intense lives. Through the process of nuclear fusion, they converted hydrogen into heavier elements such as carbon, oxygen, and nitrogen, the building blocks of planets, life, and future generations of stars. When these massive stars reached the end of their lifespans, many exploded as supernovae, dispersing these newly formed elements into the surrounding space, thereby seeding the cosmos with the raw materials for subsequent stars, planets, and eventually, life. Meanwhile, gravity continued to gather stars into larger structures, gradually forming the first galaxies, which became the fundamental building blocks of the universe. This epoch represents the cosmic dawn, the moment when light first illuminated the universe and when the processes that would shape its large-scale structure, and ultimately the conditions for life, began in earnest. Over the course of billions of years, the universe continued its dynamic evolution, with successive generations of stars forming from clouds of gas enriched by the explosions of earlier stars. Within these stellar nurseries, gravity caused gas and dust to coalesce into planetary systems, with planets orbiting newly born stars. Around 4.6 billion years ago, our own Sun formed from such a cloud in the Milky Way, accompanied by a swirling disk of gas and dust that eventually condensed into the Earth and other planets of the solar system. On our young planet, conditions gradually became suitable for the emergence of life, a process that would take hundreds of millions of years to evolve from simple microorganisms to the complex ecosystems we see today. This stage illustrates the remarkable continuity of cosmic evolution. The elements forged in the hearts of ancient stars were recycled into new stars, planets, and ultimately living organisms, connecting the vast history of the universe directly to the origins of life on Earth. As the universe continued to evolve, galaxies did not remain isolated. Gravity caused them to gather into increasingly larger structures. Galaxies formed groups, which then assembled into clusters, and further into superclusters, connected by vast filaments of gas and dark matter, creating the intricate cosmic web that defines the large-scale structure of the universe today. Meanwhile, the expansion of space itself did not slow down as once expected. Instead, observations showed that this expansion is accelerating, driven by the mysterious force known as dark energy, which makes up roughly 68% of the cosmos. It is within one such galaxy, the Milky Way, that our solar system and Earth formed, placing us within a tiny corner of this immense, evolving, and accelerating universe. This perspective highlights both our cosmic insignificance and scale and our unique ability to observe, understand, and find our place within the grand architecture of the cosmos. The ultimate fate of the universe remains, honestly, one of cosmology's most profound questions, with several possible scenarios depending largely on the nature of dark energy, that mysterious force driving accelerated cosmic expansion. One possibility is the heat death, or Big Freeze, where the universe continues to expand forever, gradually cooling as stars burn out and galaxies drift apart, leading to a dark, dilute, and, well, ultimately lifeless cosmos. Another scenario, known as the Big Rip, envisions an extreme acceleration where dark energy tears apart galaxies, stars, planets, and eventually even atoms, ripping the very fabric of matter itself. In contrast, the Big Crunch proposes that the expansion could eventually reverse under the pull of gravity, causing the universe to collapse back into a dense, hot state, which could, perhaps, be followed by a new expansion. Some models, suggest endless cycles, where the universe repeatedly expands and contracts in a cosmic rhythm, creating an eternal sequence of births and deaths. The precise future hinges on the properties and behavior of dark energy, a force we barely understand, making the universe's destiny, really, one of the greatest unsolved mysteries in modern science.